Client-side prediction gives you snappier movement, better physics, and makes cheating a lot harder. That's why we're excited to introduce PurrDiction, the new client-side prediction system for PurrNet. In online games, your input takes time to reach the server. That delay is what causes lag. Client-side prediction solves this by letting your game guess the result of your input instantly, without waiting for the server. It keeps gameplay responsive, and if that guess turns out wrong, it'll just correct it later. If you want to work with prediction, it's important we first understand how the logic of prediction runs, so we can probably utilize it, debug it, and design around it. And to really set the tone and understand the underlying problem that prediction is trying to solve, we have to take a step back. When making a single player game, interactions between objects are all ran locally, meaning they're instant to your system. This is what allows proper and fast response from every interaction. But with networking, we don't have that luxury, given we have various levels of ping. Essentially, the time it takes for data to move between your computer and the server. Now, if we don't need the benefits of prediction, this isn't a problem with normal networking. Given that we deal with ownership and the owner is the source of truth, everything will feel instant to the owner. But this does mean that everything that players see that they don't own is essentially delayed by a certain amount depending on their ping. And this is one of the major problems that client-side prediction aims to solve, or at least mitigate. It's important to understand that networking will not be perfect within any foreseeable future. So client-side prediction is essentially a technique we use to essentially hide or mitigate some of these issues that we see with normal networking. Remember when I mentioned that we don't have the luxury of instant movement with networking? Well, that's actually what prediction does, or at least emulates. The rough idea is that everyone is simulating the game locally, given the last verified state and input of the game. This will of course have various timing issues, and it's exactly this that makes up the difficult part of prediction. Now luckily for you, PurrDiction aims to make this much easier and a more automated task. But let me try to visualize for you how the logic runs behind the scenes. You as the client will essentially receive verified information represented as these green beans here. And this information arrives every tick. This is information that the server has already confirmed and will utilize in its own simulation, meaning that this information you can 100% trust as good and true to the game. So everything from this information and backwards is completely valid, and we don't have to do more with it. Now obviously, given our ping, we'll be some ticks behind. Let's take a simple case of running at 10 ticks per second with a ping of 300 milliseconds. This is obviously a rather extreme scenario, but it will work well to explain the logic. Now this would mean that you're 3 ticks behind the verified information. Now keep in mind that only clients need to do this prediction. The server essentially runs the real simulation as input arrive. And as a client, you already have your own input, so there's no delay there. You only need to predict for objects you don't control, or correct yourself if a previously predicted state turns out wrong. In games like Rocket League, this is often called rubber banding, when it looks like something happened, but it didn't. So we'll have to predict the future of other clients, and what we can do is take the received input and extrapolate some information from that. In general, with input, it's fairly safe to assume that the input will stay the same for multiple ticks. For example, if your player is moving to the right, you'll likely continue doing so. Now using this information, we can play the simulation further into the future, or essentially try to predict the future given our previous state and input. So if we are 3 ticks behind, we'll have to simulate our movement 3 ticks extra beyond the verified state. And that's essentially what you're seeing a representation of here. The green is the verified state, the yellow is the predicted tick 1 and 2, and the blue is the resulting 3rd tick, or essentially the final point of our prediction. Now, this obviously looks pretty jittery. If we just isolate the blue capsule here, you can see what it would actually look like. We'll have to smooth this. And most commonly, this is done by handling the functionality and the visuals individually. So the functionality, such as colliders, will remain on the blue capsule in this case, but the pink capsule holds all the visuals, making for smooth visuals with rather precise collision detection. Obviously, this whole thing is still a pretty big simplification of what's actually going on behind the scenes, but hopefully now you have a bit of a better understanding as to how prediction actually runs. Now let's get into actually using prediction in your project. So I have to start from a point of assuming you're already familiar with PurrNet. Other than the basic network manager setup, forget everything you know so far. For now, let's not get into mixing prediction and normal networking. They are 2 entirely different workflows, so I'm serious when I say that I don't want to see people asking about RPCs or sync vars in prediction. They don't mix well. Of course, you can utilize both in your game, but in order to avoid confusion, we'll stay completely away from it for now. As a general rule of thumb, anything that impacts prediction should also be predicted. Now, given you already have your network manager set up in your scene, let's get set up with a prediction manager as well. And we might as well add the predicted player spawn in there. Of course, you can easily handle your own spawning too, but it's easiest for now to just use the one coming with PurrNet. The prediction manager holds a few things that's good for you to know what does. The physics provider is our way of modularizing the physics system. You can make your own physics providers, but we'll also be adding more in the future, for example for fully deterministic physics. If you're making a 2D game, you'd likely want to set it to the Unity Physics 2D, but for my case, I'll keep it on just 3D. The update view mode setting allows you to easily change if visual handling in general should be done in update or late update. This will make a bit more sense later when we get to actually look at the code. The built-in systems relate to Prerdiction's own systems behind the scenes and which ones will be registered. You're generally safe to just keep everything on here, which is also why it's that by default. The predicted prefabs will have to populate. You can very easily make a new one by simply clicking the new button here, and it'll automatically create it for you and populate the field as well. This needs to be populated with all the predicted identities that you'd ever want to spawn, and in general it should just auto-populate itself, similar to the network prefabs on the regular network manager. Now, setting up a player should likely start with two things. Make an empty game object, that'll be your player, and as a child of that, make an empty game object, and that will be your visuals. So remember how I said that we disconnect functionality and visuals? Well, that's exactly what we're doing here. So anything visual should go under the visuals object, and anything functional should be on the player or a child of the player, as long as it's not a child of the visuals. This way we can entirely disconnect visuals from the simulation in order to keep everything smooth. So for simplicity, I just want to start by making the classic rolling ball game, where we later can add collision events, shooting, pickups, and more. So I'll start by adding a sphere under the visual object, so we now have a body for our player. And now we can also go ahead and add the predicted rigid body to the root of the player. And now a few things have happened. First of all, the predicted transform has also been added. The predicted rigid body and predicted transform are really just helpers to make your life a bit easier. They aren't super advanced behind the scenes, but they do make your life easier when it comes to working with physics and visuals. The predicted transform is what will be responsible of keeping the visual smooth and functionality of moving the transform working. And the predicted rigid body is what automatically handles predicting the physics such as the velocity. Other than that, it also helps you with the collision events to work with prediction easily, and we'll get into that later. Now go ahead and drag the visual game object into the graphics field of the predicted transform, and immediately it'll tell you there's a potential issue. This is because we left the collider on the sphere body that we set up, and going back to what I've said before, we need to disconnect functionality and visuals. So go ahead and hit remove on the predicted transform. This will automatically remove the invalid component here. And now we can easily just add the sphere collider on our root object as well. And let's visually ensure that it still aligns. And yep, that indeed seems good. And that's pretty much it. Now we have the base of our player set up working with predicted physics and smooth movement. If you'd want generally interactive physics objects in your scene, this is the exact same setup. So let's go ahead and make our player into a prefab and ensure it's been added to the predicted prefab scriptable. Now with our player as a prefab and in the prefab scriptable, let's remove it from the scene. We can also go ahead and drag and drop him into the player prefab field of the predicted player spawner. This will essentially handle spawning the player using the predicted hierarchy with ownership given to the client who joins. We'll be looking into predicted object spawning and despawning later on, so don't worry too much about that now. Let's also quickly go ahead and assign a few spawn points to the player spawner. Now let's go ahead and hit play. We should see the player object spawned at our first spawn point, and not much more is really happening. So let's get into making a simple movement script. Let's make a new script and call this player movement. Working with prediction, you'll be inheriting from the type called predicted identity. And it's important to understand that there are a few different versions of predicted identities available. There are the simplest ones, which are static identities, essentially for when something that doesn't actually need to simulate anything still needs to exist in the predicted game. For example, good for static world objects, which you will still need to explicitly collide with. But for the most part, don't worry too much about this one. Next, we have the stateless identity. Similar to the static identity, this doesn't hold any state, but it does, however, simulate. This allows you to easily still handle logic during simulation, given you don't need to hold any state information. Next up, we have the predicted identity with type state. This holds a state and can dynamically change its state. And quickly skipping on to the last one is the predicted identity with type, state, and input. And this is the one that's relevant to us right now. But before I move on, let me quickly explain what I mean when I say state and what it means in context to a predicted identity. So you know in your game how you want to keep things dynamically changing. For example, you want to keep track of a timer or health or essentially anything you'd normally keep in a private field and modify on the fly. With prediction, you'd want this to reside inside your state and not as a locally tracked value in your script. The reason for this goes back to the whole intro to prediction. The logic is constantly changing state and reconciling back to validated information from the server. And by keeping this in the state, we can successfully receive this validated information with the state, which is what is crucial to essentially keeping your prediction accurate. So moving onwards, let's now set up our predicted identity that takes a state and input type. You can have these structs wherever you want, but I prefer keeping them inside the scope of my script and just naming them state and input. So start by making a new public struct, name it state, and have it inherit from iPredictedData of its own type of state. You'll now see that the IDE is angry at you, and this is because you need to include the dispose method in there. By just holding Alt and pressing Enter while your cursor is on the struct, your IDE can very likely auto-populate this for you. Don't worry too much about this for now, we'll get into the dispose method later on, but for now we don't need to do anything with it. Now let's also go ahead and make the input, so make a new public struct, call it input, and have it inherit from iPredictedData. Now with these, we can go back to the original inheritance of our movement script, and have it utilize our new state and input structs. Now once again, it's expecting some overrides in here, so let's go ahead and have the IDE populate these for us. This will give us the simulate method, which is what we should use to actually run the simulation of the player. But we also need to override the getFinalInput method in order to actually populate our input. So first things first, let's populate the getFinalInput. Only the controller of the predicted identity will get this called, so all we need to do is modify the referenced input struct. For now, I think all we need is a direction of movement. So let's make a public vector2 and call it direction. Now, in our getFinalInput method, we can popularize the direction value with a vector2 for our direction. Keep in mind that you can use any input system with prediction. There's no limitations, there's no reason to, because input isn't networked. In this case, I'll just be using Unity's old input system as it's easy to test with. So making the direction have a new vector2 with the horizontal and vertical direction for movement. Great, and that's all we need to handle input. Now in the simulate method, notice how you get a state and an input as parameters. If you're going to be doing anything, this simulate loop essentially needs to be fully enclosed, meaning if you make changes to state, do it to the reference state that we get here. And if you need to use input, use the one that we have available here as well. Don't go and use input.getKey or something in the simulate. Do it through the input struct. And as long as you stick with those rules, everything should mostly be as easy as single player development. So now let's make a reference in our script to the predicted rigid body, and also let's serialize a field for move force. Now inside the simulate, let's start by making a vector3 move direction and populate it with our directional input multiplied with the move force. And now using the predicted rigid body as you would with a normal rigid body, we can just do add force and feed it the vector3 move direction which we just made. And that's it. In just about 30 lines of code, you should have fully functional predicted movement working. Let us quickly go ahead and just set it up on the player. So let's add the player movement script to the player, and let's just feed it its own predicted rigid body. And now also just so we can properly see it move around, I would just really like to add a little testing material for our player. So I'm just going to go and make a new material, player test. I'm going to add that to the body of the player. I'm going to add the default checkered gray texture just so we can actually see it rotate. Set the tiling to 2 and 2. And let's just give it some kind of color that we'd like him to be. For example, could be a clear yellow color. And now I already have multiplayer play mode set up, which is part of Unity's package. You can use this or parallel sync, whatever you'd like. And it's very easy to just start up, and here we can test it. So you can see right now they spawn up there. I haven't really set up the camera, but they both work. Now that I click onto the other window, I can move around the client, which is here, and the server is this left one. And as you can see, interactions and collisions between them also work. Now you have very clean physics in multiplayer. And it's really that easy with PurrDiction to get set up and get everything running. Hopefully you like our approach to prediction, and I can assure you there's more to come. Join the Discord to stay up to date and interact with some awesome people. The system will only get better from here. And as always, please do leave a like, comment, and subscribe. And I just hope that you have a wonderful day.